Okay guys, our next big topic is called circular motion. It's going to get split up into lots of little topics that are all really closely related. So we're going to start with just basic circular motion. We'll then move on to gravitational fields and orbits, which are obviously sort of circular motion. And then we will add in something called simple harmonic motion, which is very closely related to circular motion. Don't mind the tearing, the chinchillas are just having a run whilst I do this. First thing I want to talk about is how we measure angles. And you may or may not have thought about this, but do you know why there are 360 degrees in a circle? The answer is because 360 is a really nice number, and that is it. It's completely arbitrary how many degrees there are in a circle. We just picked a number that divides into lots of things very, very easily to make life easy. What's actually more useful than using degrees is to use radians. So hopefully you all should have come across the idea of measuring angles in terms of radians, but I just want to quickly go over it because we will be using these. So radian is something that's defined. Radians are something that are defined as based on the qualities of a circle. So a radian is the angle swept out at the centre of a circle when an arc length S is equal to the radius of the circle. So basically, when this arc length here is the same as the radius of the circle, then the angle that's been swept out is 1 radian. So it means something real. Basically, if S equals R, then my angle is 1 radian. And that leads to us having the idea that if I've got the circumference of a circle as being 2 pi r, then 1 radian is going to be 360 degrees divided by 2 pi, which is going to be 57.3 degrees. So basically, 360 degrees is 2 pi radians. This should not be new to you. You will have done this in maths, I am quite sure. So there will be some practice questions on this if you haven't already done them. I know a couple of you already have, which is great. So just some other ones that you're going to want to know. So 2 pi is 360, pi is 180, 90 degrees is pi by 2. And just as a general rule, arc length equals r times the number of radians that you've got, which is hopefully obvious given that we've defined a radian as being when the arc length equals r. So if I have more than a radian, I'm going to have that many multiples of r as being my arc length. We won't use that too much, but it's useful to have anyway. So uniform circular motion, that's what this is all about. So what we need to consider is an object that's going in a circular path. We're going to assume that it has a radius of r and a constant linear speed. So if the circumference of the circle is 2 pi r, the time taken to complete one circle of the period is the time period, capital T. That would lead us to the equation that V equals 2 pi r by T. So this, sorry about that guys, crazy chinchillas, never mind. So as I was saying, the linear speed is equal to 2 pi r by T, because 2 pi r is just the distance it travels, and T is the time it takes to do that. So it's just a real simple distance divided by time thing. Okay, so just to illustrate, if I have got my object going round in a circle, its velocity is always going to be at right angles to the radius, you can see as it goes round. And its velocity is going to be, the direction of its velocity is constantly changing. So even though it's got a constant speed, it will always have a changing velocity, because obviously you remember that velocity is a vector quantity, so the direction really matters. So it's just that we've got this constantly changing velocity. Okay, do it a few more so it goes all the way around, never pointing in the same direction. Okay, so next up we have got, I'm going to throttle them, I swear. We done? Okay, so centrifugal acceleration. So if we have an object moving along a circular path, it's constantly changing direction. So if its velocity is constantly changing, because its direction is constantly changing, it must be accelerating. So that means that we have an acceleration. Now that acceleration is going to always act towards the centre of the circle. So even as it rotates, the acceleration is always directed towards the centre of the circle, and that is called the centripetal acceleration. And the way we would calculate that is by doing v squared by r. So that's our second equation that we'll have met so far with this. So if I said we've got a centripetal acceleration, that means that there must be a force causing it. And that force is called the centripetal force. I want you to be really careful about the language that you use. You're probably going to be really tempted to talk about a centrifugal force because it's something that's commonly talked about. However, it's not a real force. It's kind of an imaginary force. It's not real. So we are never going to talk about it in terms of the A level. It's only ever going to be the centripetal force that we're going to talk about. Now, if we talk about forces, that means we kind of need to do a little bit of review of some of the stuff we met at AS. Oh, that horrible synoptic thing, remembering stuff from more than 1 year. So let's have a little look. First thing we think about is Newton's first law. Succinctly put, it says that if a body is accelerating, there must be a resultant force acting on it. And Newton's second law basically says that the direction of the resultant force must be the same as the direction of the acceleration. So basically what this is saying is that if I have a centripetal acceleration, then I must also have a force directed towards the centre of the circle. So I'd have a centripetal force in order to cause my centripetal acceleration. So if we look at a shot putter, and this wire, this bit here, that is causing the centripetal force, which allows it to turn the circle, which gives you the centripetal acceleration. Okay. So if I have an object that is moving in a circle, because it has a centripetal force, the moment I remove that centripetal force, the object is going to move off at a tangent to the circular path. It's just going to keep going in a straight line the minute that centripetal force is removed. And it will be a tangential path that it would follow. Okay, I am just going to go wrangle the monsters. And whilst I do that, I just want you to take a little second to decide what the centripetal force might be in each of these four situations. Okay, so if we have a little look then, the Earth stays orbiting the Sun because the centripetal force is provided by the gravity of the Sun. Cars go around bends in the road because of the friction on the car's tyres. Airplanes can turn because of the push of the air on the airplane's wings, and the reason that an electron orbits a nucleus is because of the electrostatic force, because of the opposite charges. So we have one final equation. This is the equation for centripetal force, and it just comes from Newton's second law of motion, which you all should remember is F equals ma. Now, however, if our A is a centripetal acceleration, then our F is a centripetal force. And we said earlier that we could find centripetal acceleration by doing v squared over r. So that gives me my centripetal force as being mv squared over r. Just thought I'd show you the little monster that's been causing all the noise, making it very hard for me to record. Anyway, if you have any questions, just remember to ask when you see me in class, and we will go over this really, really shortly. Okay? There are going to be lots of questions on this. There's lots of stuff that build and link, so it's a good one to get your head around. Okay, so I will see you in class. Don't forget to ask me questions if you got them.